Now today it's about fly ash, so I have put some presentation together with a company called Baumineral, which is actually a German company taking care of the byproducts of the coal burning plants in Germany. And my friend Christoph Maybaum, who is actually running the plant there, gave me some ideas of what to present. And I want to do this to you now. So, what is fly ash? You probably know this all. It's a byproduct of the energy industry, and it's a fine-grained combustion product built up of silicium mostly and aluminum, and you have a lot of iron there, therefore it's normally gray. And depending on the coal you are using, we heard this today, the different products have more silicium or aluminum in it. And this starts with the chemistry, because silicium with the calcium hydroxide or Portlandite of cement will give you calcium silicate hydrate, which is a cement binder. And the second cement binder will be the the calcium aluminate hydrate. So these products are pozzolanic, therefore they are reacting with the free lime to give some binders. Much more important also is that they are spherical particles compared to metakaolins, which are platelets, and they have their pozzolanic properties. Now, compared to what we heard this morning, we are taking the fly ash away in a continuous way from the coal burning plant. So what you see here in the middle is the burner. Here you have the coal milling facilities, which are here injected to heat up the gases, which go up to 1,300 degrees. And this heats up the water here, which goes through turbines to produce electricity. Here we have we try to get out the nitrogen, and here in this part you can see filters. So these filters are actually electrostatic filters, and on these filters there is a certain vacuum. So when the gases pass by, the small particles of the fly ash are filtered on the top of the filter, and from time to time the vacuum is reversed, so they will fall down here into this cyclone to be separated. And as this is happening in the warm atmospheres, we are very happy not to have to dry the material. Here then the material goes into a spraying tower where we spray lime slurry on it to bind the sulphates, and out comes here gypsum, which is called the reagips, or reagent gypsum. And here the flue gases go out into a chimney, which we will show later. So actually the distribution of the fly ash can be very different depending on the coal. So we normally try to use one coal only to in the different plants, so that we can control the quality of the fly ash. We have now the fly ash is doing different things. It evens the distribution, it gives less sedimentation in the concrete, it fluidifies because it has ball-bearing effect on the mix. Therefore, you can use less water to get the same consistency of the concrete, and we can densify by this the concrete. It is chemically reactive and it has a pozzolanic activity. And if you look at the picture on the left, you will see these fly ash particles in the concrete. And that means if there are two cores, that there is not enough time to dissolve the particle to react it. This is what we see on the right side. There is a Blaschke made some papers on that. You can see that on the surface of the fly ash particle, there is a reaction. On this side, rather less. But in the end, it remains quite a filler. So when we discussed with Christoph once, because we are transporting this thing over 1,000 kilometers sometimes to Austria, we thought that all these coarse particles would be rather a filler and not a reactive particle. And we discussed how can we now make out a more reactive fly ash of it. And we have read in the literature that the fly ash and beneath diameters of 10 microns mostly can be dissolved and reacted with the calcium hydroxide. So what we actually wanted to do is to separate the fine part of the fly ash and get under 10 micron or under 20 micron. These smaller particles have more effect even on the fluidity. Therefore, it is a big help to make concretes with a very dense matrix and with a high reactivity. Actually, Microsit 10 is almost as reactive as a slow metakaolin. Because the surface is so big and the dissolution is so strong. Now, here we have the particle size. The black one is the normal SEM 52.5. The fly ash normally has a rather lengthy curve and ends up to 300 microns. That's why it is not dissolved before the concrete is hardened. Microsilica is very fine and is quite reactive. The problem with microsilica may be that you cannot add too much because the surface is so big that you have a problem and the material becomes sticky. The Microsit is between the cement and the microsilica, and here we have a curve from about the Microsit 10, so you can see it's a very even distribution, and the medium value, the D50, is around 3.5 to 4 microns, which is as fine as a metakaolin would be. So this is the standard grade we have is the Microsit 20 and the Microsit 10. That means everything in the Microsit 20 is under 20 microns and the Microsit 10 is under 10 microns. We classify these fly ashes through air. It's an air classifier. And we can modify very easily the particle size by using a faster or a slower airflow. For certain application, we have a Microsit 90, for example, for self-leveling compounds. We have a Microsit 50, depending on what the customer really needs and wants, and the price, naturally, because the finer you get, the more expensive it becomes, and the rest has been to be used in concretes which have not the quality which we want and we apply. Actually, Baumineral is I guess, the biggest producer of fly ash in Germany and probably in Europe. Now we analyzed what can be done with the Microsit, and here we have a slice on the left side of a standard concrete, and you can see the yellow is the pores actually you get into the normal concrete. And if you look here at the rim of the aggregate, you will see that mostly you have a rim on the aggregate because the binder will shrink and the calcium hydroxide will be the last thing which is precipitated on this surface. That means that if you put that thing on the water, it will slowly swell or dissolve here, and you have a lot of ingress of material. On the other side, here we used about 20% replacement of SEM1 with Microsit 20, and you can see the difference in the binding. It is a very dense mortar, and you can see that here on the rim we have a much smaller rim, and breaking the part away, you can see that we even succeeded in having a crack in the quartz particle. Therefore, you have a good glue for your aggregates, and that will strengthen your material and concrete. So we also, because naturally we are finer than cement, we can fill the cavities between the cement, which should be these particles. You can also fill this naturally with Microsilica. But here we have Microsit 10 and Microsit 20. And if you have the right proportion, you can fill these voids in your binder in a quite cheap and good way. The higher density will give you a reduced water uptake and will also help you to reduce your water binder quality. If you have no ingress of water in a concrete, then normally the acids or salts or sulfates as well have a much slower migration because they all need water to migrate. And therefore, you get here a better seawater resistance and a better resistance to de-icing salts, which I will explain a bit later. And the durability will naturally be increased because in the end, what you want is a homogeneous concrete where the binder has about the same strength as the aggregate, which is normally not the case. Now, here we measured the stability on the sulphate stress, and you can see that with an ordinary Portland cement, you have a change of length which is very high. If you replace the 25% with a normal fly ash, you are here lowering a bit the system. With the Microsit 20, you're about the same. With the Microsit 10, because it is much smaller than the cement particle, you can see that you have a length change which is extremely low. So this is what we were looking for, and I'll bring you some examples later. The same thing happens with the chlorine diffusion. So if you are using normal fly ash and then you look at your chlorine diffusion measured through concrete, you will find that the chlorine diffusion is quite high. If you use Microsilica, you will find it is very low. Here we had some deterioration, I don't know exactly why. But with Microsit 10, you can see that you can reduce greatly your chlorine migration in concrete. Now I show you some application and some case studies to give you an idea why and what we are doing with that. So in Germany, we had a canal here for the wastewater, which was with about over 50 kilometers long. It was in the open and smelling very badly. So actually, people started to think we should put it under the earth, which actually has been done. So we had to produce about 35,000 concrete wastewater pipes with a rather high resistance against sulphuric acid because the pH of the water was very low. There was a lot of sulphate in it, and because the pipes are very dense, they are not getting attacked, and they should last for many years. Here we have the chimney of a power plant. In the past, we had to coat this with epoxies because the pH was so low. And today, with the dense formulation we have here, which is here, we have a fly ash and we have Microsit, and we mix the both. We have some quartz sands in it, etc. We get a good compressive strength after 28 days. Freeze thaw is good. The pore radii are very low. And here we look at the acid resistance at pH 3.5. You can see that we have a very low mass loss. Therefore, we could avoid to use epoxy coatings, which had to be replaced every few years. Here you have the classification of the concrete, which is extremely high in resistance against de-icing salts, etc., chemicals. One of an easy application was for the Hungarian railways, where they have a sort of a concrete fence so that the people won't run over the rails. And the problem there was that they were using standard concrete with steel rebars in there, which was quite heavy. And the overlay of the steel had to be quite strong. But still, as you can see, the fences were easily destroyed. These fences had to be laid down by a crane because they were very heavy, and you had to use a lot of trucks. We then decided to try to make a new construction way using cement and Microsit here, and using polypropylene and glass fibers, so that we came down from about 8 centimeters thickness to 2.5. These elements can be laid by 2 people on the place, and because they are very lightweight, you don't need so many trucks. And in the end, because you don't need so much material, you are sparing on cement, sand, and other aggregates, and you have a good CO2 reduction, and you become cheaper. Therefore, the Hungarian railways decided to use these systems for the future. I believe when we look at the future, we should not only look at the cement, we should look at what can we do with concrete, and because we have to rethink also the concrete and not only the cement. And the slimmer the parts become, and if the effectivity of the object is still there, we should try to go to these elements. Now we, because of the denseness of these concretes, we have made up formulation for petrol stations, where you have naturally also de-icing salts in the winter when the tires of the car bring it to the petrol station. On the other side, you may have leaks and petrol which is spilled on the surface. The denser the concrete is, the less problems you will have to clean it, and the less attack you will have on the cement. Naturally, also from a mechanical point of view, if your concrete is very dense, the abrasion resistance is much better, and the same thing is the abrasion resistance of the mortars. So here we have again the high fluidity and the self-compacting concretes. As I said before, you can have a good flow and no separation, which is needed especially in self-compacting concretes. Concrete for seawater buildings, concrete for clarification plants, because also there you don't want to have the water seeping out of your plant. We use it in floorings or self-leveling compounds because it gives a very good abrasion resistance and it gives a good strength also. And we are trying today also to replace a lot of steel, because rebars, the production of rebars produces about twice as much CO2 as the production of cement does. So wherever you can replace your rebars because of the quality of the cement, you're on the winning side. We also use it in grouts, and we use it naturally in high performance concrete or ultra high performance concrete. This is one of the last application we had. It's a half pipe, and naturally you have here the same problem, is that if you have the quartz settling and the cement flowing up to the surface, the abrasion resistance will be terrible, and the poor kids which are running over there probably will have a problem making their arts in this application. Well, let me summarize. I mean, you can get high density with fly ash, but if you have a classified fly ash and you are going into the fine particle size, you can get your density up, and the compaction of the concrete will be much better, giving you a higher strength in your concrete. Because it is very dense, sulphate and acids cannot penetrate your concrete, and therefore you have a very good resistance. Because you have this ball-bearing effect, you get a better workability, a better flow of your material, and you can use a lower water demand, maybe even sparing some fluidifying agent, which would make it cheaper. And because you are very dense, you have a less shrinkage, especially if you replace quite an amount of your Portland cement, which is shrinking, which is autogeneous shrinkage, or with a drying shrinkage later if you have a lot of pores. In the end, I must say, as shown in the beginning, these fly ashes we collect quite economically. So it's not, and the cement price going up because of the CO2 taxes, I believe we come to a very good economic situation. We had a problem with fly ash the last years because the German government decided to close down all the coal plants. In the meantime, it is the reverse. We have to reopen a lot of plants, and we had to find the coal to run them. So for the moment, we have enough fly ash, and especially as these classified fly ashes are not as a cheap byproduct, but are really giving you a good advantage in your concrete and are a bit more expensive, naturally. I believe we have enough material which we can sell on the market and which bring us the future to a lower CO2. We can prolong the life cycle, which will be also a very important point. Most of our final customers today ask for a 100 years life cycle, at least. That means we, for example, for bridges or shotcrete or things like that in tunnels, we have to guarantee today 100 years. And with mixes of fly ash, slag, and metakaolin, you can even go up to a 200 years life cycle, probably. Though we cannot watch for 200 years, but there are some formula and some institutes working on it, and they can predict, I hope, also the time of a concrete life cycle. The slimmer parts is really to use less material, to use less sand, because also sand today has become a problem. And in any case, also quarries today, opening a quarry is becoming more and more complicated. People don't like to have many quarries in their backyards. So if we use less material, that is good. And we spend less energy. So I hope I gave you a decent overview, and I thank Christoph Maybaum for his cooperation and collaboration to make this presentation. And I'm absolutely happy to help you with further information. I did not want to put too many data and tables on the floor, but you can always contact me at technical@muchem.org, or here's my mobile phone. And we have, actually, we have a homepage, which is a Muchem info. And we have also a homepage for metakaolin info. And we have a homepage for anti-shrink info, because we believe that also the cracking of concrete, if we can eliminate this, we can eliminate a lot of rebars and steel in that.